Good day, everyone. We are going to discuss scientific theory on Tyndall scatter. There are several videos on Tyndall scatter. However, they don't apply to smoke measurement, and I thought I needed to do a deep dive into this because it's very influential information for smoke measurement. A lot of this information has not been fully scrutinized or fully criticized and fully tested or validated. It's a start to a process. This is a scientific process in process where we hypothesize what we think is going on and we allow other great minds with great tools to either contradict or validate this information. So we'll be talking about smoke measurement using Tyndall scatter, using Mie and Tyndall scatter theory. This is the opacity and color shift from a recent test I did. I was using bark and branches, and take a look at the step up in the color shift. You can see it, let's see, I put fuel on at 30 minutes and then at 1 hour intervals, with the right side of the graph being a large load when the stove was cold. So the red line indicates a color shift in the color of light received by the sensor, and you can see that with each fuel load, that color shift steps up. And I thought that was indicative of small particles smoldering in the post-peak phase of the fuel. You also notice that the opacity, which is in blue, steps down and actually under zero for the last phase. And that's a problematic reading that we have to explain. I made this diagram to help explain what I think is going on. So as you pass light through smoke, if your particles are PM 2.5 down to 1,000 or even 400 nanometers, they're under the rules or under Mie scattering or May scattering, depending on how you pronounce it. I've been told to pronounce it May scattering, but it's spelled Mie scattering. This is because the wavelength of light is smaller than the particle. And so when it strikes a particle, it gets under the rules of Mie scattering, May scattering, and generally will behave in one way, blocking all the light, or in some cases doing different things. However, when the particles are less than the frequency of light measured in nanometers, you're under the rules of Tyndall scattering. So that would include anything under 400 nanometers for a 400 nanometer light source, and would be measurable down to 40 nanometers. 10% of the wavelength results in a scatter under Tyndall scattering guidelines. Now, just to make sure everybody understands just how small this is, a nanometer is 1/1000th of a meter. So these are extremely small particles. The reason this is important is under the opacity measurement principle, we can use the Mie scattering. However, on the color shift portion of the measurement, I believe the rules of Tyndall scattering are in effect. In other words, we're not measuring opacity in this region. We're measuring particle count of very small particles. Typically in this phase, when we see a large color shift and low opacity, it's because the particles, the emissions leaving the chimney are so small we can't see them. They don't appear to be present when we look at the smoke coming from the chimney. It's quite clear. The opacity may be negative, and the color shift is often significant and measurable. And so I think there's a large number of these smaller than 400 nanometer particles leaving the chimney, and that's scattering the light, resulting in the color shift. This chart is one that I've developed. I call it the percent of max, and to me it tells the story, but you have to understand how the data is plotted. So on this test I ran for about 4 hours and I put wood in for 4 hours. However, this chart is 24 hours of data. So after I stopped putting wood on, you can clearly see where I stopped putting wood on. Now let's say 123 hours. And I'll explain the time. The octaring had been on for many days before I ran this test. So it's demonstrating that it can be run for many, many days and provide data. Well, what I want you to look at is the blue line. The blue line is the blue diode, and it's percent of max signal for this run. Blue line is suspended or diminished down below the other diode signals. And that is because of Tyndall scatter. So smoke being a colloid, when the particles are smaller than the wavelength of the light, then the particles are scattered and away from the sensor. So that's a lack of blue light hitting the sensor. So you can see from 123 hours to 130 hours. That's what, 7 hours of data where I was only burning for 4 or 5 hours, and here we have 7 hours of data where we're putting out unknown quantities of small particles. You can't see anything in the chimney or coming out of the chimney. It's just hot gases. But I believe what we're measuring here are the small particles. How many? I don't know. We have to come up with a way of validating that. But I think the data is clear. Let's say you don't believe the blue line. The gray line right above it is the clear diode, which incorporates all red, green, and blue light. You can see that it as well is diminished in the light received by the sensor. To give you an idea of how much data is here, the blue line normally would be 20,000 counts and is down 1,500 counts. So that's a significant signal. Also, the data looks very clean. The noise in it is very small, and it always produces the same data, through that 124 to 130 hours. I'm going to bring in another graph. It's the same data set, but you're going to be looking at it from a different perspective. This is the same data, and we're seeing the blue is the opacity, the red is the color shift, and that's the combined RGBC diodes calculating the color. All those lines and the lack of blue light reaching the sensor offsets the color into the red. Think about a sunset on a smoky day. As the sun drops on the horizon, it turns red. And that's because the blue light is being scattered by the smoke. And so what your eye receives is the red light from the sun. Don't be looking at the sun. But in this graph, you can see for about 4 or 5 hours, we put wood on the stove and we had a step up of the color shift, which is explained by scattered blue light, and it's measurable and significant at 123 hours. Then almost comes back to zero at 144 hours. So that's what? 20 hours? 20 hours our chimney appeared to be burning clean, yet was putting out these very small particles. Now, these could be just a few particles, and they're very small, billionths, measured on the billionths of a meter. However, I believe we are detecting them, and they are measurable. The real question is, how many particles are there, and are they significant? Particles this small would go up into the sky, and the first chance they were to condense in water would condense and drop them out of the sky. So I don't think they're going to be hanging around in the air very long. However, I believe we have a way of measuring them. Now, it's going to take much better minds and tools than mine to validate this. We would have to take samples of the emissions and use microscopic scanning electron microscope or other methods to see particles this small and count them. This is not an easy task, and this is all theory at this point. This is the scientific process at work, where I've developed a method for measuring and a readout, and we have to find out in real life, or in real sciences, the physical sciences, what is comprised in the atmosphere leaving the chimney, in the emissions leaving the chimney, that would result in a color shift of this magnitude. Now let's try to explain the negative opacity. So it's fairly typical to get a negative opacity when you have a large color shift. And that's difficult to explain, but I'll give it a shot here. Mie scattering is kind of interesting in that when light strikes a particle, in some situations, it scatters forward. I don't know how to explain that other than Mie scattering is rather strange. Think of the sun when it goes behind a cloud. Sometimes you get a halo around the sun, and don't be looking at the sun. When you get that halo around the sun, that's Mie scatter scattering forward. So there are times when the light can pass through the emissions better than air. It's usually not by much. I've not seen it over 5%, but 2 or 3% is routine. I see that routinely, usually when there's a large color shift, like in this test. So I run this test out all the way to 24 hours because I wanted to come back to baseline. It could be a lot of particles, but it may be only a few particles. And the particles are really small, and they probably don't go very far before they are condensed out of the atmosphere and deposited on the ground. So I don't want to cause concern that wood stoves are putting out way too much particulate matter. I'm saying I'm measuring something. I don't quite know exactly what it is, and I'm debating with the science team on what it could be and trying to work toward validation with some other measurements to determine what is actually going on here. In this graph, what we have is the max color shift. There was an event many hours into it that offset it down a little bit, but I think the well, there's a reason for the 105 reading. So this is several days of data. So each line number on the bottom is 24-hour interval. And what I'm looking for is during the day when the sun comes out and heats up the octoring, and then overnight it gets colder, how is that changing the light readings? And then at the very end of the data is when I ran a test had a fire in the wood stove. So you can see the contrast when it's just collecting data, and it's collecting data every 20 seconds. We see that, well, on one day, the blue did fall down quite a bit. But on another day, clear came down more. So they do diverge. And this is generally the LED changing its light output ever so slightly. And it's something we have to work with. Being on a chimney, it's going to get hot at times, and sometimes it's going to get really cold. So it has to work through a large color range. However, you can see that when we do run a test, the data is a little different. So you can see that large blue color shift at the very end of the data. So this really is to show that over 5 days or so, the data is actually pretty good. It does change at night and during the heat of the day when the sun is impacting it, and it does change when you have a fire in it. I like to collect baseline data because it tells me the baseline noise level of the system. All right, if you just didn't have enough of charts, here's another one. So this is the alpha octaring that's been sitting out on it. And what I have displayed here in the yellow line is the LED temp. I track the LED temp because if it goes too hot, it'll degrade. So it's not the environmental temperature. It's sitting on a heat sink by an energized LED that can reach 150 degrees. But it does give us an idea of that position's temperature fluctuation. So in the middle of the night on a cold day, it's still running at 100 degrees Fahrenheit, or down to, let's say, I see about 88. But it will run even without a fire in the wood stove. When the sun's baking on it, it'll run up to 140 degrees. And it's got air running through it, but that's still why I want to watch it. I don't want to see it go over 150. Now, it is impacted by the heat in the wood stove, not in this chart data. This is, well, there's no fire in the wood stove, but you can also see how the temperature fluctuations impact color shift, which is the red line, and opacity, which is the blue line. And these are really close to zero. Let's see. Opacity goes up to 4, positive 4, and a negative approximately 3. Color shift just it dropped down to negative 15. So it shifted to the blue a little bit. It's not really reading any particles. There's no smoke going out the system. So this is just baseline data. So it's important to understand the baseline data of an instrument so that you can understand when you have good readings, good data. So you can subtract out the baseline. So you could take an average and a standard deviation of this data set. There are probably 20,000 data points on each of those lines. So this is really good data for understanding the tendencies of your system. I found an image to help describe Mie scattering or Mie scattering. And the image on the right indicates that when the light strikes a particle, that there'll be more forward scatter than backscatter. So it's not completely blocking the light. It's striking a particle, and some of the light gets pushed forward. Now, when I'm measuring smoke and I have a lot of color shift, I have these occasional times when there's a negative opacity indicating that there's sensors receiving more light than it does during baseline. And that's difficult to explain because in common sense would tell you, hey, there's smoke, there should be less light. Well, Mie scattering or Mie scattering indicates that in some situations you get slightly brighter light. Just look at the arrows. The arrows indicate more light, and they get longer in the direction of the light. It's something to think about, that there is documentation that Mie scattering increases the amount of light forward. Now we'll change to the Tyndall. So the Tyndall effect only happens in colloids. Smoke is a colloid. And when you project a light through a colloid, it behaves differently. A colloid is often very small particles within a liquid or a gas. So smoke is solids and liquid particles in a gas. It's suspended in air or the gas coming out of a chimney that is mostly air, but is quite different than the air we breathe. So if you shine a light through water as a solution, it goes straight through. There's no scatter to the side. When you shine a light through a colloid like smoke, you get a lot of backscatter. If you shine a light through a suspension like flour in water, you get some side scatter. It'll generally, if you get the particles the right size, it will scatter only blue light. So it works in a narrow region, and smoke is within that region. I'll find another graphic that's helpful.